Okay, so now we will solve the same example, that is the 2x2 linear convolution where SP is equal to HP into XP, and HP is given by H0 plus H1P and XP is given by X0 plus X1P. That same problem we will be implementing using modified Cook Toom algorithm. So using direct implementation, number of multiplication operations required were 4, addition operation required were 3, and that reduced to 3 using Cook Toom implementation, but addition operation increased to 5. Okay, now we will implement it using modified Cook Toom algorithm, and we will see that what are the number of multiplication and addition operations required. So step 1 is to choose L plus N minus 2 different real number. So L is 2, total number of terms present in HP, and N is also 2. So L is 2, N is also 2, and L plus N minus 2 is 2. So you have to choose total 2 real numbers, that are beta 0 and beta 1. Okay, so let beta 0 is equal to 0 and beta 1 is equal to minus 1. You have assumed some small integer values. Step 2 is to compute h of beta I and x of beta I for I equal to 0 and 1. So for I equal to 0 and 1, beta I is 0 and 1, and h of beta I will be h0 plus h1 beta I, and x of beta I will be equal to x0 plus x1 beta I. Okay, so putting I equal to 0, h of 0 is equal to h0, beta I is equal to 0, so this term will become 0. So h of beta 0 is equal to h0, and h of beta 1 is equal to, beta I is equal to minus 1, so h of beta 1 is h0 minus h1. Similarly, x of beta 0 is x0, putting beta I equal to 0, and x of beta 1 is equal to x0 minus x1, putting beta 1 equal to minus 1. So in step 3 you have to compute s of beta I, that is equal to h of beta I into x of beta I for I equal to 0 and 1. So s of beta 0 is equal to h of beta 0 into x of beta 0, that is equal to h0 dot x0, and s of beta 1 is equal to h of beta 1 into x of beta 1, that is equal to h0 minus h1 multiplied by x0 minus x1. Okay, so don't multiply this bracket at this instant. Step 3, is to compute S prime beta I, that is equal to S of beta I minus S of L plus n minus 2 beta I to the power L plus n minus 2. Okay, so L plus n minus 2 we have already calculated, that is 2, so we have to calculate S of beta I minus S of 2 beta I square. So coming to the direct implementation, where SP is written as S0 plus S1P plus S2P square, and the right hand side is the product of H of P into X of P, that is equal to H0x0 plus H0x1 plus H1x0 into P plus H1x1 P square. Okay, so comparing this two sides, S2 is equal to H1x1. Okay, so that we have to substitute at this equation. So that is equal to S of beta I minus H1 x1 beta I square. Okay, so we have to compute S prime beta I, that is given by S of beta I minus H1 x1 beta I square for I equal to 0 and 1. So S prime beta 0 is S of beta 0 minus H1 x1 beta naught square. So beta naught is 0, so this is equal to S of beta 0, that is H0 x0, and S prime beta 1 is equal to S of beta 1 minus H1 x1 beta 1 square. So beta 1 is minus 1, so that is equal to H0 minus H1 into x0 minus x1 minus H1 x1, and minus 1 square is plus 1. So in the next step you have to compute S prime P using Lagrange interpolation formula. So S prime P is given by S prime beta naught P minus beta 1 divided by beta 0 minus beta 1 plus S prime beta 1 P minus beta naught divided by beta 1 minus beta naught, and substituting beta 0 is equal to 0 and beta 1 equal to minus 1. S prime P is S prime beta naught plus P into bracket S prime beta 0 minus S prime beta 1. So in the next step you have to calculate S of P, that is given by S prime P plus S of L plus n minus 2 P raised to power L plus n minus 2. So L plus n minus 2 is 2, or we have already calculated, and S of 2 is equal to H1 x1. So substituting this value, we have S prime P plus H1 x1 P square, that is S of P. and the left hand side can be written as S0 plus S1p plus S2p square, and that is equal to S prime p plus H1 x1 p square. So substituting the value of S prime p here, we have S0 plus S1p plus S2p square, that is equal to S prime p is given by S prime beta 0 plus p into S prime beta naught minus S prime beta 1 plus H1 x1 p square. So this equation can be represented in terms of matrix. So in the left hand side we have a column matrix and the elements are S0, S1 and S2, and on the right hand side we have S0 is equal to S prime beta 0, S1 is equal to S prime beta 0 minus S prime beta 1, and S2 is equal to H1 x1. Okay. So we can further decompose this matrix, separating the terms S of S prime beta 0, S prime beta 1, H1 x1 to one matrix and their coefficient to other matrix. So we can write S0, S1, S2 on the left hand side, and on the right hand side we have S prime beta 0, S prime beta 1 and H1 x1. And since this is a 3 cross 1 matrix, 3 rows are mandatory, so 3 rows are also mandatory for this matrix, and number of column will be also equal to 3, so that they both can be multiplied. So their coefficient, so the elements of this matrix can be derived very easily. Okay, so in the first row I need only S prime beta 0, so S prime beta 0, so corresponding value of first row first column should be 1 and remaining value should be 0. Similarly in the next row the elements are 1 minus 1 0, so this gives S prime beta 0 minus S prime beta 1, and in the last row I need only H1 x1, so correspondingly I have 1 at row 3 column 3. So we can replace now S prime beta I with S of beta I, so S prime beta 0 is equal to S of beta 0. From this equation you have already calculated S prime beta 0 is equal to S of beta 0, and S prime beta 1 is equal to S of beta 1 minus H1 x1. So S prime beta 1 is equal to S of beta 1 minus H1 x1. So substituting this value to this matrix, we have S0, S1, S2 on left hand side, and on right hand side we have 1 0 0, 1 minus 1 0, 0 0 1, and S prime beta 0 is S of beta 0, S prime beta 1 is S of beta 1 minus H1 x1, and H1 x1 as it is. So this matrix can be decomposed into two different matrices. One matrix will contain element S of beta 0, S of beta 1 and H1 x1, and the second matrix will contain the corresponding coefficients constant. So S0, S1, S2 will be equal to this matrix with 1 0 0, 1 minus 1 0, 0 0 1, and we have separated s of beta 0, s of beta 1, and h1 x1, and its coefficient can be determined very easily. Okay, so s of beta 0 in the first row, so the value are 1, 0 and 0. So this is a 3 cross 1 matrix, and this will be a 3 cross 3 matrix. Second row consists of 0, 1 and minus 1. So 0 into s of beta 0 is 0, 1 into s of beta 1 minus h1 x1. So that is s of beta 1 minus h1 x1. And in the third row we have 0, 0 and 1. So 1 into h1 x1 gives h1 x1. So these two matrices can be multiplied. So the result will be 1 0 0, 1 minus 1 1, 0 0 1, and we have already calculated s of beta I. So s of beta 0 is h0 x0, s of beta 1 is h0 minus h1 into x0 minus x1. So we can replace the values of s of beta I with their calculated values. So h of x0 x0 is equal to s of beta 0, and s of beta 1 is equal to h0 minus h1 into x0 minus x1, and h1 x1 as it is. And further we can decompose this matrix. Okay, so we have 1 1 0, 0 minus 1 0, 0 1 1 as it is, and I will separate terms of x into one matrix, that is x0, x0 minus x1 and x1, and the terms of h into another matrix. So this is a 3 cross 1 matrix, so it should be a 3 cross 3 matrix, and its element are h0 into x0, remaining terms will be 0. This is this term is 0, this term should be h0 minus h1 into x0 minus x1, and this should be 0, and this should be 0 0 h1, and finally decomposing this matrix. Okay, so decomposing this into x0 and only x1. So I have s0, s1, s2 on the left hand side, and matrix 1 0 0, 1 minus 1 1, 0 0 1 as it is, and h0 0 0, 0 h0 minus h1 0, and 0 0 h1 x1, and separating x0 and x1. So this is a 2 cross 1 matrix, so the coefficient matrix should be 3 cross 2, 3 rows and 2 columns. So the values of this matrix can be easily determined, and it is 1 0 1 minus 1 0 and 1. So this is x0, this calculation corresponds to x0 minus x1, and this calculation corresponds to simply x1. Okay, so this term is calculated. Okay, so this is a pre-computation matrix, this is post-addition matrix. This consists of the constant coefficients, and this matrix consists of a signal element. Okay, so the computation carried out are as follows. So computation carried out are in step 1, this constant coefficients can be pre-computed, so I can write capital H0 is equal to h small h0, capital H1 is equal to h0 minus h1, that can be pre-computed, and capital H2 is equal to h1, that is pre-computed. So in step 2, the subtraction or addition of signals that are coming from the external source can be calculated. So I can write x0, capital X0 is equal to small x0 as it is, capital X1 as x0 minus x1, small x0 minus x1, and capital X2 is simply x1. So this can be done by the pre-computation matrix. This calculation will be done by pre-computation matrix. So in step 3, capital S of beta I will be calculated, and that will be achieved by the result of this 3 matrix. Okay, so in step 3, capital S0 is H0 into capital X0, that is H0 into X0. S1 is equal to capital H1 into capital X1. This is H1 and this is X1, and S2 is equal to H2, capital H2 into capital X2, that is H1 into X1, H1 into X1. Okay, the fourth step, we have to perform the addition of the calculated terms. That will be done by this pre-addition matrix. So small s0 will be equal to capital S0. So S1 can be written as 0 capital S0 minus capital S1 plus capital S2, and small s2 is equal to simply capital S2. Okay. So total number of multiplication operation are, this is 1 multiplication, multiplication 2, and multiplication 3. So multiplication is 3, and addition operation is, this is addition 1, this is addition 2, and this is addition 3, 1, 2 and 3. Okay, so this convolution can be implemented by performing 3 multiplication operation and 3 addition operation. So compared with the direct implementation and Cook Toom implementation, modified Cook Toom implementation needs 3 multiplication and 3 addition. Okay, so you can see that addition operation is same, multiplication operation is reduced by 1, and when we compare it to the Cook Toom implementation, number of addition operation is reduced to 2.